So, in the last class we are discussing about arithmetic group of instructions, 8086 instructions. So, in that we have discussed about the addition instruction with and without carry, subtraction instruction with and without borrow. So, the next arithmetic operation is multiplication. So, the multiplication instruction is like mul. So, we can give register slash memory. So, you have to specify register slash memory after the mul. So, the operation inside this one is so for 8 bit by 8 bit multiplication, we can have 8 bit by 8 bit multiplication or 16 bit by 16 bit. For 8 bit by 8 bit multiplication, you have to specify the register 8 bit register or the memory location 1 byte. So, this is one operand, the contents of either 8 bit register or from memory 1 byte has to be multiplied with the other operand will be by default in register AL and the result is also by default stored in AX. So, whatever the register or memory that is specified in the memory instruction, that will be multiplied with AL contents and the result is stored back to AX. For example, if I take, so before this if I give AL as 5, some CL as 10, H, these are hexadecimal numbers. If I write mul CL, by default the other register is AL. So, the multiplication of this one will be, so the result will be there in AX. So, what will be the result? The hexadecimal multiplication of these two numbers. Okay, we can directly perform the hexadecimal multiplication also, or otherwise you convert these numbers into decimal, you perform the multiplication in decimal number, convert back the result to hexadecimal. So, 55 hexadecimal is equivalent to, what is the decimal? 5 into 16 plus 5, which is equal to 85 decimal. 10 is 10H is 16 decimal. So, if I multiply 85 by 16 decimal multiplication, $860 is the decimal value. So, if we convert back this 860 to hexadecimal, 860 you have to successfully divide with 16. 16 5 is 80, 60 will be again 16 5s are 80, 60 will be 4, 3 will be 48. So, what is the remainder? 53 16s, the remainder is 80, 60 is 48, 12 C, and 16 3s are 48, 48 remainder will be 5, 16 zeros remainder is 3. So, the answer will be 35CH. 860 decimal is equivalent to 35C hexadecimal. You can add 0 also here. So, this contents of AX will be 035CH. This is how the multiplication will perform. So, we can give here instead of register, we can give the memory also. Which memory again? The memory can be accessible by using any one of the addressing modes that we have discussed in the earlier classes. This is for 8 bit by 8 bit multiplication. For 16 bit by 16 bit multiplication, So, you have to specify the register 16 or a word from the memory. This is one operand. The other operand will be by default the contents of AX, and the result will be by default stored in two 16-bit registers DX comma AX, because if you multiply two 16-bit numbers, the maximum result will be 32-bit. So, this 32-bit result will be stored in two 16-bit registers. In that, most significant 16-bit will be stored in DX and the least significant 16-bit will be stored in AX. This is about the 8-bit by 8-bit multiplication, 16-bit 16-bit multiplication, but this multiplication is called unsigned multiplication. Here we will assume the numbers, the data to be unsigned numbers. So, on the other hand, we have signed multiplication also, because in 8086 we will use the signed representation, signed 2's complement representation. So, the only difference between this mul and signed multiplication is the mnemonic for this signed multiplication is imul. Same thing, you have to specify register slash memory. So, again for 8-bit by 8-bit multiplication, we have to use AL contents of register 8 slash memory byte, result will be stored in AX. This is exactly same as that of unsigned multiplication. The only difference is here the data will be given in signed format and the results also will get in the signed 2's complement format. If I take an example, so I want to multiply minus 15 into plus 5. The expected result is minus 75. So, then how to give this data? You take this minus 15 into one of the registers, either AL or any other of the register or any memory location. You take the plus 5 into the other register and you multiply. So, how to take, if I want to take this minus 15 into some BL register say. So, what has to be loaded into BL? The microprocessor understands only ones and zeros only, it will not understand the minus sign. So, for that, so minus 15 has to be represented in first signed 2's complement representation. So, in case of signed 2's complement representation, because this BL register is 8-bit, we have to represent 8-bit form, because we are going to store this in 8-bit register. If you want to store this minus 15 in 16-bit register, we have to represent minus 15 in 16-bit signed 2's complement form. Okay. So, here I am using 8-bit because I want to store this in BL. So, MSB bit in signed 2's complement representation, the MSB bit is always sign bit followed by magnitude bits. This is 1 bit and this is remaining 7 bits. So, for negative numbers MSB bit is 1, for positive numbers MSB bit is 0, and for my 15, so what is the 7-bit binary form of 15 is 0 0 0 1 1 1 1. So, this is called signed 1's complement representation or signed magnitude representation. Signed magnitude representation. There are 3 ways to represent signed numbers, but in microprocessors we will use signed 2's complement representation. This is called signed magnitude representation. Whereas in signed ones, MSB bit is 1 because of negative number. You take the 1's complement of this is 1 1 1 0 0 0 0. This is called signed 1's complement representation. Then signed 2's MSB bit is 1, you take the 2's complement of this means 1's complement plus 1. So, this will be 1 1 1 0 0 0, you have to add 1 to the LSB. This is called signed 2's representation, signed 2's complement representation. Now what is the hexadecimal equivalent of this minus 15? Then this will be F, this will be 1. So you have to take BL with F1. So if you want to perform the multiplication of minus 15 into plus 5, so you have to load this F1 into BL. And what about plus 5? Plus 5 will be in sin 2's complement representation, MSB bit and magnitude bits. MSB bit will be for positive number 0, magnitude bits for 5 will be 7 bit equivalent of this 5 will be 0, 0, 0, 0, 1, 0, 1. If the number is positive, all the 3 representations are same. So this is in all the 3 combinations, signed magnitude as well as signed 1s, signed 2s. All the 3 representations are same if the number is positive. So these representations will be different only if the number is negative. So what will be hexadecimal this now? If I take this 0, 0, 0, 0 as 0, this is 5, 0, 5H. Then to perform this multiplication, the instructions will be, so I want to take 1 into BL. So move BL comma, so minus 15 in sin 2's complement representation will be F1. And move, one of the operands should be in AL for 8 bit by 8 bit multiplication. So AL with the second number which is plus 5 is 0, 5H itself. Then write mul BL. So inside this AL and BL will be multiplied, result will be stored in AX. Now what will be the contents of AX after this instruction? So in decimal form, the result will be minus 75. Here we will get in AX 2's complement representation of minus 75. So what is the 2's complement representation of minus 75? Minus 75 in 2's complement representation, sin 2's complement representation. Will be MSB bit is 1. If I take this sign magnitude representation, 75, what is the binary equivalent of 75? 75 you can convert into binary, 2 3s are 6, 7 is 14, so 1 remainder, 2 1s are 2, 2 8 16, 1 is the remainder, 2 9 0, 2 4s are 1, 2 2s are 0, 2 1s are 0, 2 0 1. So you have to read from bottom to top. So the magnitude bit will be 1 0 0 1 0 0 1. This will be 1 0 0. This is sign bit. This is magnitude. 1 0 0 1 0 1 1. This is in signed magnitude representation. But the result will be in sin 2's complement representation because we have given the 2 datas in sin 2's complement representation. So from this signed 1s will be, you have to take the 1's complement, this remains 1, this will be 0 1 1, 0 1 0 0, signed 1s. Signed 2's means you take again add 1 to this, signed 2's will be, we add 1, if I add 1 this MSB becomes 1, 0s 1 1, 0 1 0 1. So what will be the result? The hexadecimal equivalent of 1 0 1 1 is B and 0 1 0 1 is 5. So you will get 0 0 B 5. This is about the signed multiplication or any signed arithmetic. So in signed arithmetic, whether it is addition, subtraction, multiplication or division, so you have to take both the operands in sin 2's complement representation and you will get the result also in the sin 2's complement representation. So this is the difference between mul and imul. So imul is for signed multiplication, this is signed multiplication. Similarly, we have division for unsigned numbers, division for signed numbers. Div, The next instruction is unsigned division, div. Again you have to specify register slash memory. Memory can be byte or word. Register can be 8 bit or 16 bit. This is called unsigned division. Here also we can have two types of the divisions. It can be either 16 bit by 8 bit division, or it can be 32 bit by 16 bit division. For 16 bit by 8 bit division, divisor will be by default in AX. So, this will perform the operation like AX will be the divisor always, dividend is AX, divisor will be the 8 bit register slash register 8 bits or memory byte. Then we will get quotient and remainder. So, this performs and this will store the remainder in AH, quotient in AL. This is the division operation. Division register 8 slash memory. This is 16 bit by 8 bit division. By default dividend will be in AX, and divisor we have to give either 8 bit register or memory byte. So, after this division, remainder will be stored in higher order 8 bit register of AX, which is AH, and lower order 8 bits quotient will be stored. Similarly, for 32 bit by 8 bit division, so the dividend will be 32 bit register, which is combination of two 16 bit registers DX and AX. This is by default. And then divisor will be 16 bit register contents or memory word. Again the result of this one, the remainder will be stored in the higher order register, which is DX, and quotient will be stored in AX. This is about 16 bit by 8 bit division and 32 bit by 16 bit division. Similarly, we have for signed division we have IDIV. We have to specify register slash memory. This is called signed division. So, the operation is exactly same, except for that here all the data has to be represented in signed 2's complement representation. I have given one example for the multiplication. So, here I will not give any examples. So, in a similar manner you can perform this division also. This is about the division, unsigned division and signed division. So, these are the four important arithmetic operations: addition, with and without carry, subtraction, with and without borrow, multiplication for unsigned numbers as well as signed numbers, division for signed numbers as well as unsigned numbers. So, these are the four important arithmetic operations. The next arithmetic operation is increment and decrement operations. INC is the mnemonic for increment operation. So, we can increment the contents of register 8. So, simply the operation is the contents of register 8 will be incremented by 1 and stored back to same register. If I take the example, if AL is FFH, if I write INCAL, so what will be contents of the AL after this? Will be 0 0. Why? Because FF, if we add 1, this becomes 1 0, this becomes 1 0. So, the 8 bit result will be 0 0, but carry flag will be set. Similarly, you can have 16 bit register increment also, INC register 16. So, the 16 bit register contents will be incremented by 1 and stored back to same 16 bit register. Similarly, you can increment the contents of a memory location byte from the memory location, INC memory, which you can take as byte, or INC memory word. So, you can take a word from the memory location, again the memory location will be specified by one of the previous options that I have given. What are the 5 options we can specify the any way to access that particular memory. These are about 4 increment instructions. Similarly, we have 4 decrement operations. So, we have DEC, mnemonic for decrement is DEC, register 8 means register 8 contents will be decremented by 1 and stored back to same register 8. Similarly, you can have DEC register 16, register 16 contents will be decremented by 1 and stored back to same register 16. We can have DEC memory byte, so the contents of the memory byte will be decremented by 1 and stored back to same memory location. And you can have decrement memory word. As I have told, word is 2 bytes. So, the contents of the memory location memory word will be subtracted by 1 and result is stored back to the memory. So, these are the 4 increment and decrement operations. So, the next arithmetic instruction is, this is one of the very important instruction, which is DAA, decimal adjust AL after addition. This instruction operates only on the register lower order register AL. So, that is why the addressing mode here will be implicit addressing mode. There are some instructions which operates only on a specific register. Those all instructions belongs to implicit addressing mode. Here also this DAA operates on AL only. So, we know that after the addition, if I want to perform the BCD addition, basically this will be used in BCD additions. So, if I take say for example 2 BCD numbers, move BL comma 09. Even though if I give this BCD number, the microprocessor will take only hexadecimal data, this will assume that this is hexadecimal. But the ordinary layman, he knows that this is only decimal 9. Then if I take move AL comma 05H, and if I write add AL comma BL, the operation is contents of BL will be added with contents of AL and the result is stored back to AL. So, what will be the AL contents? Because this the microprocessor will take as hexadecimal numbers. If it perform hexadecimal addition, this is 14. So, this AL contents will be 0EH. But the user, the ordinary layman, he expects 9 plus 5 should be 14. Okay. So, to get this 14 from this AL, that is 0E, we can write DAA. After DAA, the contents of AL becomes 14. which is the BCD addition of 9 plus 5. So, how this operation will be takes place? So, what is the internal operation that takes place inside the DAA is, so this internal operation is, if the lower nibble means lower 4 bits of AL is greater than 9, or if auxiliary carry flag is set, this instruction adds six. This instruction adds 6 to the lower nibble. And second one is, similarly it will check for higher nibble also. If the higher nibble of AL is greater than 9, or if carry flag is set, this instruction adds 6 to upper nibble. If I take the same example here, so if I add this 09 plus 05, 09 H will be 0000 1001 and 05 will be 0000 0101. If I perform the addition, 1 plus 1 is 1 0, 1 1 1 0 0 0 0. You check the lower nibble result. What is the result of lower nibble? This is 13. There is no auxiliary carry flag, but if either of these conditions satisfies, either auxiliary carry flag is set, or if lower nibble of this one is greater than 9. So, because this lower nibble, this value is greater than 9, this is 13. So, this instruction what happens, this will add 6 to this lower nibble, whereas this one is either carry flag is set, this result is greater than 9. So, the microprocessor, this instruction DAA instruction will not add anything, only 0 0 0 0 will be added. So, what will be result now? So, this will add, because greater than 6, add 6. So, what is the result? 0, 1 plus 1 is 1 0, 1 plus 1 plus 1 is 1 1, 1 plus 1 is 1 0, 1 0 0 0. This is nothing but 1 4. So, this was actually this 0E. As I have told here, the contents of AL will be 0E, because the microprocessor assumes that these two numbers are hexadecimal numbers. But what I want is, I want BCD result. Okay. So, if I pass through the DAA, the contents of AL becomes 14, which is the addition of BCD addition of 9 and 5. So, this is the operation which takes place inside this instruction DAA. So, it will check the lower order 8 bits. If this magnitude is greater than 9, this will add 6, or if the auxiliary carry flag is set, this will add 6. Similarly, higher order 8 bits, if there is carry flag, or if higher order 8 bits is greater than 9, this instruction will add 6, otherwise nothing. So, then we will get the final result in BCD. I will take an example where auxiliary carry flag is set, magnitude is less than 9. If I take the second example, suppose if I want to add something like 39H, 48H. So, what is 39H? 39 plus 48. So, I want actually decimal addition. If these are decimal numbers, what is the expected result? 9 plus 8 is 17 and this one is 8. 87 decimal is expected. But microprocessor will take 39 as hexadecimal number will take this one as 0011, 1001, then 48 also it will take as hexadecimal number. So, the corresponding binary is 0100, 1000, and it will perform the addition. This is 10010. This magnitude is less than 9, lower order nibble, but there is auxiliary carry flag because there is a carry from this position to this lower nibble to upper nibble. So, auxiliary carry flag is set. So, because of this instruction adds 6, and here this will be 1 plus 0 plus 1 is 10, 10, 10, 1. This is neither of this condition is satisfying. This magnitude is 8 which is less than 9, and then there is no carry flag, carry flag is reset. So, this instruction simply adds 0, 0, 0, 0. So, if I write the instruction like move AL comma 39H, move BL comma 48H, if I write add AL comma BL, the contents of AL will be, it will give the hexadecimal result which is nothing but the hexadecimal result is this, only this 81H, this will be 81H. But what is expected if I write DAA, after this AL will be having the corrected decimal result will be 87. So, you can see here that after addition you will get 87, 1 1 1 0 0 0 0 1. So, this is 8, this is 7. So, this is how we can use this DAA instruction. So, whenever you want to perform the BCD addition or even BCD subtraction, there is other instruction. For BCD addition, if you want to adjust the result as a BCD result from the hexadecimal, we can use DAA instruction. Similarly, we have next instruction which is called DAS, decimal adjust AL, same thing but here after subtraction. Same thing here, this will perform BCD subtraction, this will be used in BCD subtraction. So, if this auxiliary carry flag is set, this instruction subtracts 6. If auxiliary carry flag is set, this instruction subtracts 6 from lower nibble. Similarly, if carry flag is set, this instruction subtracts 6 from upper nibble of AL. This also instruction will be only for AL region. This is implicit addressing mode. Here there is no question of this result is greater than 9, because this is some in BCD subtraction, we have to give only BCD numbers. We cannot give here, remember that you cannot give here A, B, C, D, E, because this is decimal, means BCD. So, this should be 0 to 9, this also should be 0 to 9, this also 0 to 9, this also 0 to 9. If I perform the subtraction, the maximum value of digit is 9. If I subtract the subtraction, we will get only the value which is more than 9 only. So, if I take an example here also, if I take the same 48 minus 39, I want to perform the decimal subtraction or BCD subtraction 48 minus 39. So, what is expected is 9, 0, 9 decimal. But if I give these values, move AL comma 48, it will take as hexadecimal by default, move BH or BL comma 39, it will take by default as hexadecimal. Then if I add these two, add AL comma BL, then after this the contents of AL will be, so whatever this hexadecimal subtraction value, that will come. So what is 48? 48H will be 0 1 0 0 1 0 0 0 minus 39, H will be 0 0 1 1 1 0 0 1. So as you are discussing about this different flags of microprocessor, auxiliary carry flag will be set during the addition if there is a carry from lower nibble to upper nibble. During the subtraction, if there is a borrow from upper nibble to lower nibble, in that case also auxiliary carry flag will be set. Here if I want to subtract 0 minus 1, so you have to take the borrow. So if you take the borrow, this becomes 2, 2 minus 1 is 1. Again to perform 0 minus 0, no borrow is required, but already this has given one borrow to this one. To pay that, it has to take again borrow. So this becomes 2. Out of this, 1 has been given to this one. So 1 minus 0 becomes 1, and this also again same thing. So 0 minus 0, no borrow is required, but it has given 1 to the previous stage. So to pay that one, it has to take a borrow, so that it becomes 2. Out of these 2, 1 is given to here, and 1 minus 0 is 1, and this 0 has been given, this 1 has been already given. So this becomes 0 minus 1. To perform 0 minus 1, this has to take borrow from upper nibble. Borrow is required from upper nibble. So borrow is required from upper nibble to lower nibble, implies auxiliary carry flag is set. So after taking the borrow, what will be the result? This will becomes 2, 2 minus 1 is 1. Again here 0 minus 1, it requires a borrow, 2 minus 1, already 1 has been given here. So 2 minus 1 will be 0. This also 0 in a similar manner. This is 1 has given 0 minus 0 is 0, 0 minus 0 is 0. So this will be the result that we are going to get, which is nothing but 0 and F. So the AL will be having 0 F. But what is the decimal result that we will expect? 0 9. So if I write DAS, so what this instruction will do is, as I have told, so this will check the lower order 8 bits. So this is more than 9, and auxiliary carry flag is also set. This instruction simply subtracts 6. So this will, instead of adding, in case of DAA it will add 6, whereas here it will subtract 6, 0 1 1 0, and this is neither carry flag is set nor this magnitude is greater than 9. So it will subtract 0, simply means no change. So this has to be subtracted. So if I subtract 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1, 0 0 0 0. So what will be this? 0 9, this is the correct result. After this DAS, AL will contain the BCD subtraction result, which is 0 9. This is how we can perform the BCD addition and BCD subtraction using DAA and DAS. There are 4 more instructions, so which are called AAA. These are also for addition, subtraction, multiplication and division, but they are on ASCII operation. So the previous one is on BCD, whereas these instructions are for ASCII. This is ASCII adjust after addition. So we know the ASCII code, we have discussed it in the earlier class. ASCII is American Standard Code for Information Interchange. So correspond to this keys 0 key. If I press the 0 key, the corresponding decimal hexadecimal digit will be 30H will be generated. 1 means 31H. So on up to 9 will be 39H. Similarly, correspond to alphabets, we have standard code. So this ASCII, if I want to perform addition, ASCII numbers addition, without masking the 3, we can perform the ASCII addition. So the ASCII addition can be performed without masking this 3. This 3 is extra, this is 0 actually, BCD, but 30H is the hexadecimal, this 3 is extra. So, without masking these 3 also we can perform the ASCII addition by use of this AA instruction. ASCII addition can be performed without masking. Three in the upper nibble. So, how this will be performed? For example, if I want to add ASCII characters 9 plus 5, I want to perform 9 plus 5 ASCII addition. So, we take this 1 into accumulator AL, this also will adjust AL, this also works on only register AL only always. If I take AL as 39H, which is ASCII code correspond to 9, this is using move instruction, I am not writing that. Then BL say 35H, this is the ASCII code correspond to 5. Okay. So, if I write add AL comma BL, so what will be the result? It should be 39 plus 35, which is equal to E6, 6EH. So, after this AL will be having, because the microprocessor assumes only hexadecimal data, as I have discussed in the earlier instruction also. Even if you give this BCD number, it will take a hexadecimal. Even here if you give ASCII number, it will take a hexadecimal, and it will give the hexadecimal result, which is 6EH. But I want this as 1-4. So, this will give, if I write instruction AAA, the contents of AL becomes 0-4. Why 0-4 is 9 plus 5 is in fact 1-4. So, the lower this is carry flag will be set, and the result is only 4, because this AL is 8 bit register, this will store only 8 bits. So, this 16 bit result is cannot store, but carry flag will be set here. So, if you want this result in ASCII, so what is the addition of this one? It should be, so 9 plus 5 should be 14. So, for 1 the ASCII code is 31H, for 4 ASCII code is 34H. Okay. To get this 34H, we can do it ORing with, we write something like OR AL comma 30H. I am going to discuss this OR instruction in the logical group. This is very simple, only OR instruction, OR logically OR the contents of AL with 30H and store the result in AL. So, after this AL will become now, so 30H and 4H if we OR, so 30H and 04H, we are ORing this. So, this will be 0011, 0000, 4 will be 0000, 0100. What is logical OR between 0, 0? Bitwise logical OR operation. 0, 0 logical OR is 0, 0. If any one bit is 1, output is 1. This is 1, this is 0, this is 1, this is 1, 0, 0. This is 3 and this is 4. So, AL will content becomes 3, 4H, which is the ASCII code correspond to the lower order result 4. Then again if you want for the higher order also, so this carry flag contents you take onto the AL register by using the shift register, shift mean operation and rotate instructions, that we are going to discuss in the logical group. So, I can take this 0, 1 onto the AL, 0, 1, the contents of carry flag contents will be shifted to AL. For this you can use rotate and shift operations. We will discuss this rotation shift instructions in the next group, which is logical group. Then again OR with AL with 30H, so that now AL will be having 31H. So, this result 2 ASCII characters. So, 4 correspond to 3 4 and 1 31 we can store into AL. In this, of course, if you want you can move into some other register, because here you are using AL. This is how we can adjust this ASCII addition. After ASCII addition, the result will be stored back into ASCII by means of this AA instruction. So, this is the operation how this ASCII will be stored in AL. Similarly, we can have ASCII adjust after subtraction. You can write after or for, it is no problem, normally for. In a similar manner, no need to explain this. There is one more instruction for multiplication, which is ASCII adjust for multiplication. ASCII adjust, this is after multiplication. Even though this is A ASCII, this is actually BCD. Sorry, BCD adjust after multiplication. So, I will explain the operation inside this AAM. This is also another interesting instruction. Okay. So, if you want to perform the multiplication of 2 BCD digits. So, in DAA and DAS we have discussed about the multiplication of addition and subtraction of 2 BCD digits, whereas for multiplication of the BCD digits, to get the BCD result we will use AAM actually. So, if I take, say for example, if I want to perform 5 decimal 05 decimal into 09 decimal, what is the expected result is 45 decimal. Okay. This is exactly similar to DAA and DAS. Now, to perform this multiplication, I will take one of this one into AL 05, but if I give 05, this will by default take as hexadecimal, even though I have given decimal, by default it will take as hexadecimal. Similarly, if I write move BL comma 09, it will by default take hexadecimal. If I write mul BL, so we know that the inside the operation will be AL into BL and the result is stored in AX. So, what will be contents of AX after this? The hexadecimal equivalent of this 45. So, this is decimal. So, if I perform the hexadecimal multiplication, as I have told, one way to obtain the hexadecimal arithmetic is you perform the decimal and convert back to hexadecimal numbers. 45 decimal. So, this will be equal to how much hexadecimal? 45, 16, 16 2s are 32, 13, 13 is E, 16 zeros 2, so 2E. So, this will contain 0 0 2EH. But what is expected? Expected value is 45D. So, to get that 45D in unpacked BCD, we are going to use AAM. After this, AX will be having 04 in AH. After AAM, AX contents, this will be AH content, this will be AL content, is 0 5. This overall this will be AX. This is what is called unpacked BCD. So, what is meant by unpacked BCD is only one BCD digit per byte is called unpacked BCD. Packed means, if I want packed means this is something like 45. If I contain 45, this is called packed BCD, whereas 04 and 05 is unpacked BCD. This is packed this is unpacked. So, this is the definition of unpacked BCD, one BCD digit per byte, this is one byte, this is another byte. Okay. So, if you have one BCD digit, this is called unpacked. So, this AAM instruction will give unpacked BCD result of the given two numbers, multiplication of the given two numbers. So, this will be result of AX after this multiplication. So, this is also called as BCD adjust after multiplication. So, this is exactly similar to DAA, DAS. In DAA, to get the decimal addition value, we will use DAA. To get the decimal subtraction value, BCD, so we will use DAS, and AAM for getting the BCD multiplication value. Similarly, we have AAD division. I will continue this in the next class. Okay. Thank you.